viscosity and pH control. Tanks of ink can sometimes be water-based ink. Water-based ink can be both viscosity and pH sensitive. If you are working with an ink that is water-based and it is pH sensitive, we already know it's viscosity sensitive, you have to control both parameters. pH is the first to control. Viscosity is the second to control. Backwards, right? Is the second to control. As the pH increases, the viscosity will decrease and stabilize. If the pH decreases, you can actually get increasing viscosity, whereby if you added more water, you'd actually dilute it, and the ink molecules can all fall to the bottom, and they're all dead, sitting on the bottom. When the ink molecules have the right pH value, the ionic load keeps them in suspension. So the question is, you're running a printing press. You have water-based ink, or a coating, or a lacquer. What are you going to do? You can take a viscosity measuring element, you can take a pH measuring element, and you can stick them in the ink. You can also put these in a line from the ink tank to the applicator. I'm not showing the applicator here. I'm just doing a very basic tank of ink, water base, pH measurement, viscosity. You can further have a container with an ammonia solution, often called amine, which should be appropriate for the ink you're making. So talk to the supplier of your ink to ask them what you should be diluting at. Over here, you'd have a water supply, which is used for viscosity control. These are two-way valves. They wire back to the controller. These wire to the controller. The controller is actually two controllers. One half controls pH, one half controls viscosity. In the viscosity side, we put in a time delay. That's because pH is the more important parameter. So we tell the viscosity side, hey, if your viscosity is a little bit high, let's check the pH and let the pH get in balance first. Because like I said, you can reach a condition where your pH is off, your viscosity is high, you add a lot of water, and the pigment can settle to the bottom of the tank. Not a very good situation, doesn't help you to process. So the controller is measuring pH. There'd be a set point here, and the controller sees the pH rising above the desired value. It would open this valve and let some of this amine solution flow into the tank. The amine solution is a higher pH than this. Let's assume you're running 8.8 pH. You'd want this to be maybe a 10 pH. You don't want this at 14 pH. 14 pH is the most caustic level you can get. It'll shock the ink. The solution going down here will be like burning your skin with paint remover. this pH should be 1, 2, maybe 2 or 3 points above this value. If this was 9.0 and you're controlling at 8.8, the pH control loop will add so much of this amine solution, which does contain water, that you'll end up filling up the bucket full of ink and probably spilling it over. Because to get, if this is a 9 and you're at 8.8, to bring it up, you have to add a lot of material. So you want a decent differential here, not an extreme differential. This could be 10, it could be 11, in that range. So the pH control system runs along with its own timing, its own time delay, where it senses, it adds if necessary, then it waits, gives the amine time to mix in the ink, circulate through the process, come back. It can then say, okay, we didn't add enough, add some more. At the same time, the viscometer is over here measuring viscosity. And if the viscosity is increasing, the viscometer can add water. In this case, we're showing it in a tank. You could use a water feed from a pipe coming out of from the street, but sometimes street water has bad pH by itself. If you're doing pH control, you better know what the water pH is, because if the water pH is 6.5 and you're running at 8.8, adding in the water alone disturbs your pH. You just have to be, that means you have to put a higher dosage over here to offset for water additions. So this is a basic simple tutorial on viscosity and pH control. Ink, ionic charge, concentration of ions is what is a measure of pH. The ink molecules want to be in the right balance to stay in suspension, to lay down on the web, to dry right, not to tack, not to smudge, not to bleed. pH is the more important of the two parameters. Control pH first, then control viscosity. Now, we're going to go on to another topic regarding pH. A pH probe is comprised of two cells of different saline solutions. It's basically a battery. There's a plus and there's a minus. And there's a small microvolt signal coming up this wire, which goes to the controller system. This is down in the ink. As these molecules are flowing by the pH sensor, and of course these are drawn way bigger than this is. These are really small. This is totally an exaggerated size. But there'll be a slight current flow from here to here, or it might be from there to there. When you have a pH of 7, there'll be no flow. As the pH goes up, you get flow in one direction. As it goes down, in a different direction. Therefore, this signal here can be a plus or minus, very low voltage and very low impedance signal. We convert this signal into typically milliamps, and that's what we transmit to the controller, because milliamp signals are strong, 4 to 20 typically. This signal is in a coaxial cable from the sensor, which is in contact with the ink, the controller. This coax cable, if it's damaged, will mess up the signal and you're going to have problems. Anyways, the nature of pH, there's a glass membrane here. There's a plastic filler. If I was to take this membrane and blow it up really huge, there is a film on the glass membrane. And the glass is semi-porous. The film is designed so when these ions come near it, it allows electrical charge to flow through the glass. What does this mean? This means if you have a probe and you take the ink away, let the air come in and let the air dry on this, there's a film on here. The probe is no good. It's down. It's no good. You got to keep pH probes wet all the time. Whether you're in tank or in a line. If you're in a tank and the job is done, take the probe out. Have some standpipe somewhere with some fluid. Probe comes out, goes in the standpipe. Keep it wet. Change the ink, put it back in. Norcross viscometers can sit here and get dry, and they can begin functioning when they get wet again. They're mechanical. This has the glass tip. It's inherent in every pH sensor in the world. You have to keep that end wet. If you don't, or if you have sludge that comes along and covers the junction, you're going to get incorrect readings. pH is a slow-moving parameter. It changes slowly. So always wet, always clean. And if you're taking a probe out and there's wet ink on it, the best thing is to put it into a cleaning solution, because if you take a napkin or a cloth towel and you start wiping the end of this, you can damage that very thin layer. If it's coated up and dried, take a screwdriver, you can break the glass. Keep them wet, keep them soaked. When they get dirty, there are cleaning solutions available, and you'll have success with pH control. Viscosity control is old hat. This is new to those who don't know about it, and these often need calibration to match the sensor. You're going to have an operator here. He's going to have a little pH sensor that he dips in the ink to check the pH manually. These have to be synchronized up. You can calibrate this and this together on the same two buffer solutions. Buffer solutions age with time. Once you open the bottle from the supplier, they begin to decay. You have to change those on a regular basis. You have to recalibrate on a regular basis. And just like on this, there's a cap on the end. That's to keep it wet. You gotta keep this end wet. There's no cap to put in it because you're in a tank. That's why you put it in a standpipe if you're using the in-tank type sensor. If it's the inline sensor, the ink is flowing through here. When you put your wash water through here and you drain this out, in our inline chambers we have a small trap which will leave behind a small amount of liquid. This is meant for short term, not a weekend, not an overnight. if you're going down for a weekend or for a long period of time, then this whole chamber should be in some kind of piping configuration so that, obviously, as I draw this, the ink flows in, the ink flows out. The washing solution flows in, the washing solution flows out. When you're done, you can drain out here and drain out here. You want to leave washing solution all through here. So this is all kept moist. When you come back in the morning or at the end of the shift change, put your new ink through there. Keep this wet, keep it clean. If you get sludge in here, a globule of sludge, and it goes down and lodges on the end of the sensor, you can get some very funny readings. They can go high, they can go low. Makes no sense, but this is blocking that double cell I explained on the previous sheet. Sensors have to be kept wet, and 90% of our customers in a process control environment will intellectually understand this. The practical implications of operator protocol and operator handling of an in-line or an in-tank sensor. The operators are not used to treating these probes with the same. They're used to treating the viscometers rugged. These are physically rugged, but this end has to be kept wet. Management has to work with operators so both management and operators understand why you put a cap on the pH sensor in your hand, i.e. do the same thing here in a different way. So that's a brief tutorial on viscosity, pH, and some of the characteristics of pH sensors, and some do's and some don'ts. Hope to see you again on YouTube or wherever you saw the video. Have a great day. Thank you. Bye-bye.